Hello, everyone. Many people in here, and I'm also a little nervous. My name is Won-jae Yu, and I'm a graduate student of Korea Aerospace University. Before the presentation, I'm going to speak a little slow because I'm not great English, especially speaking. My research interest is a global navigation satellite system. It's called GNSS, and GNSS receiver and assisted GNSS, and software-defined radio-based pseudo-live positioning system. So I have been started the research of SDR-based time synchronization, which is core of positioning system. This research is an initial study of SDR-based time synchronization method. So let's start the presentation. This is the presentation order. First, I will present what is time synchronization and its applications briefly, and how time synchronization is performed in GNSS is also introduced. And then I will talk about our designed time synchronization method utilizing USRP and GNU radio. In addition, GNU radio companion and Python code will be also introduced. And then I will present an experiment and its result, which confirm the performance of our designed synchronization method. And lastly, conclusion with our future work will be presented. First, introduction. What is time synchronization? Time synchronization is a process of aligning to the same time reference between two or more time regions that are having different time. And also, time synchronization is a core technology in various fields using internet-based network services, such as geodesy, weather, GNSS, finance, and so on. Time synchronization can classify two methods. First, wired and wireless. And this network time protocol is called NTP, and Ethernet are utilized as a wired time synchronization method. And reference broadcast synchronization is called RBS. And timing synchronization protocol for sensor networks is called TPSN. And GNSS are utilized as a wireless time synchronization. In this research, we used an instantaneous synchronization method, so it is similar to RBS method. Next is how time synchronization is performed in GNSS. First, GNSS satellites transmit a navigation message, including the signal transmission time information. And then, GNSS receiver receives this navigation message from the GNSS satellite and synchronize to the GNSS time by decoding a navigation message. In order to keep the GNSS time accurately, 3 or 4 cesium and rubidium atomic clocks are mounted in GNSS satellite. And this atomic clocks has a highly precise oscillation accuracy. Therefore, user can estimate their position by using this highly precise oscillation, this highly precise time-synchronized GNSS satellites. However, if user cannot use GNSS signal due to jamming, blockage, and other interference environments, user should estimate their position by using other methods, such as pseudo-right or access points. And pseudo-right is not a real satellite, but replaces the role of navigation satellite. And satellites can be, pseudo-rights can be divided into this ground-fixed pseudo-right and mobile. And time difference of arrival method is frequently used in pseudo-right positioning system because receiver time does not require to synchronize with the transmitter's time. Therefore, separate time synchronization method between pseudo-rights must be needed in this case. Next, our designed time synchronization method. This is the basic concept of time synchronization. First, this time reference, it called master, generates the time reference signal and transmit it to the other slaves. And its signal transmission time is T under Tx. After that, the slaves receive a time reference signal from the master or time reference. And its signal reception time is T under Rx. So the goal of time synchronization is minimize the time difference between the signal reception time and the signal transmission time. And it is also compensated each signal's travel time. So all processes need to be implemented by utilizing USRP and GNU radio because various time synchronization methods can be easily designed by SDR. So we generated the time reference and slaves utilizing this USRP. At first, time reference generates the PPS signal as a time reference signal. The PPS signal is a mixed form of square pulse and carrier pulse. It's very simple. This pulse width adjustable square pulse is generated utilizing this cosine signal source and threshold block. After generating a time reference signal, the clock source transmits it to other slaves by using this USRP sync block. And then slaves receive a time reference signal from the time reference unit. in order to check the amplitude level of the received time reference signal, converting it to the magnitude. After converting, the slaves need to judge this received reference signal is valid. So below is the valid signal determination implemented by Python code. And its detailed explanation will be on the next slide. A dual threshold method is applied to determine a valid signal. When the time reference signal is transmitted, at first, signal amplitude is getting higher. And signal amplitude variation between samples is also getting higher. So for exceeding this dual threshold, the signal reception time is determined as the first sample time of rising edge. On the right of slide, in this case, the time synchronization is performed at the first sample time of rising edge at this point. This is the overall operational flow of our design synchronization method. Generate and transmit a time reference pulse at reference USRP, and the signal transmission and slave USRPs receive a time reference pulse and determine a valid signal by utilizing dual threshold method. After that, the time synchronization is performed at the signal reception time as the first sample time of rising edge. And lastly, the synchronized time between each slave USRPs are compared each other. Next is experiment. A simple wireless time synchronization experiment was performed. 4 ETUS USRP N210 that mounted SPX daughter board, and 4 laptop PCs, 4 ultra-high frequency band antenna were utilized in the experiment. 424.75 MHz was selected as a carrier frequency. Data sampling rate was 1 megasamples per second. We used about this 424 MHz as a carrier frequency because it is the lowest operational frequency of SPX daughter board in Korea industry, science, and medical. It's called ISM frequency band. And the distances between reference and slave were approximately 5 meters. one USRP was utilized as a reference USRP, reference unit, and the other 3 USRPs were utilized as the slave. And each experiment set consisted of USRP and laptop and UHF antenna. Reference USRP generated and transmitted a time reference signal during 10 minutes, and it equals 600 epochs. And slave USRPs confirmed of the time synchronization accuracy by comparing the signal reception time of each USRP. And synchronized time errors were analyzed by its mean and standard deviation. Sample data received by each USRPs are illustrated. And these are waveforms of received reference signal. And time synchronizations were performed at the first sample time of rising edge and in these points. In experiment, we used a low precision time reference signal compared to very precise and stable clock pulses. But I guess the main error is an operational code, which is not to optimize. And it is heavily influenced by processing speed of host PC because operational code was used the dual threshold method. Double conditional statements are quietly burdened on the host. So therefore, synchronized time error was occurred from tens to 100 microseconds. Lastly, conclusion with our future work. Conclusion. We designed and implemented a simple PPS-based time synchronization method utilizing USRP and GNU radio, and it is an initial study of SDR-based time synchronization. And it generated a USRP-based separate clock source instead of a GNSS-based clock source. Although its synchronized time accuracy deteriorates, it was confirmed that the time synchronization between USRPs can be achieved within a certain error range. However, our designed synchronization method cannot be used for pseudo-rise yet. So, and also, many works will be done in the future. And we evaluated the feasibility of time synchronization scheme by GNU radio-based algorithm, such as signal generation, transmission, and reception and processing. Future work. Time synchronization accuracy is affected by the efficiency of source code. So code optimization will expect to be necessary. It will need to use the C++ API, such as text stream block, it's called TSB, and protocol data unit, it's called PDU. This can reduce the synchronous time. And time synchronization accuracy is affected by host computer performance in terms of sampling rate. So host performance improvement will expect to be necessary too. If time axis resolution improves between samples, and more precise time synchronization will be achieved. In addition, precise detection method of a valid signal will be considered to prepare a long-distance time synchronization environment. And pseudo-random code, and it is represented as a orthogonal code, and matched filter will be considered, and message-based time reference signal, it is similar to GNSS navigation message, will be continuously considered. Thanks for listening to my presentation.
All right, let's thank our speaker. Do we have any questions from the audience? Right here. What's up, Richard?
So did you conclude that you could get, for say, a TDMA time slot boundary? Is it correct, did I read your slide right, that approximately 100 microseconds of accuracy for the boundaries?
This picture?
Yes. Is that the right conclusion from this table? What's your variance on getting time synchronized between the USRPs, basically?
These clock errors are calculated at these synchronized time errors. So we compared these synchronized time errors, its mean and its standard deviations. So we calculated these time errors are from tens to 100 microseconds. So it is a very simple work.
Okay.
Any other questions? No? Okay, thank you very much. Great job. Felix? Komm drauf.